Alright, so today we'll be seeing about computer vision using deep learning methods. So, like, I did have a recording for this, but we had a lot of crashes in session, as you might remember. So I thought I'll just make a new video on it so that it's pretty convenient for you. So today we'll be learning about the deep learning methods for computer vision. That mainly includes convolutional neural network. So we'll be learning about why deep learning method is better than classical methods as a bit of introduction, and then we'll be learning about some CNN components, what is convolution, pooling, activation, etc. And then we'll be training our own CNN on SIFT and dataset. We'll be creating the dataset too, and then we'll be learning about transfer learning. Okay, so let's move on. So, what is exactly deep learning? So, deep learning started in 2012 when AlexNet won an ImageNet competition, and he reduced the error from like 26% to 16%. And the reason why deep learning methods is better than classical methods is because there are a lot of methods in deep learning that is straight up better than classical methods, which mainly includes feature extraction method. So let's go through it. So in classical approach, what you do is you firstly extract handcrafted features. So you manually extract features from techniques like HOG, which stands for histogram of oriented gradients, or you use SIFT, scale invariant feature transform, or you use color histograms. So using all of these, you get some generic features that are designed by humans like us, and they're not optimized for any specific task. So they are not task specific. And then after we get the data set, like extracted features, you train them on a simple uh, ML model like SVM, random forest, etc. for classification. Like this is done after this, and then the image that is, for example, 256 into 256 is converted into a 1000 dimension feature vector, and then it will contain all the feature patterns, etc. And then you train a simple classifier on the dataset, and then you get some decent accuracy like 70 to 75%, for example. This is just example numbers, not any tested numbers, and they might be absolutely and relatively wrong, but just for the impact of deep learning, I chose these numbers. And then what is the difference between classical and deep learning is that in deep learning you just feed the raw images to CNNs. So you have a raw RGB pixel values from like it will be like 3 into 56 into 256. So like if you have a 256 into 256 image, then you'll have 256 into 256 into 3. So you'll have that many numbers because you're not pre-processing it. So you'll feed to like I think it comes out to be around 2 lakh. So when you multiply all those numbers, you get a feature vector, and then you directly input it into a convolution neural network. You don't need to extract any features, and that is the most convenient thing about deep learning. And then the neural network in itself will discover optimal features during training, through methods like backpropagation and gradient descent. The network will learn the best pattern for itself, and the features in itself are very task specific. So the learned features will be in this specific case, we learn how to use them for classifying the task. So for example, the network might learn to relate cat whiskers or dog snouts, or like maybe some specific some fur pattern, etc. And then we'll train it from end to end. So feature extraction plus classification is trained together as one unified model, and then optimizing it is our overall purpose. And then we just see that our performance will be improved by a lot because we didn't need to manually handcraft the features. So what is the key advantage of CNNs? like deep learning over manual handcrafting is that we don't need to actually learn the features. So classical methods require domain experts. They need algorithms like SIFT, HOG, etc. to design features, and this process might be time consuming, and they require a lot of experimentation with different methods and is limited by human understanding. So deep learning actually overcomes this bottleneck because it will learn all the optimal features from the dataset during training. And as the network will see thousands of examples, it discovers patterns that best separates the classes. So example of cat for classification in this case might be that in I might have written it somewhere. So the deep learning method in its early stage, so early neurons might fight strongly for vertical edges that might be viscous, and then other neurons might detect specific color combination, for example orange color, and then higher level neurons combine these to detect viscous patterns near faces, so complete objects, scenes, etc. So that's how hierarchical neural network works. So these are known as uh, hierarchic, hierarchical representations. So CNNs can learn features of multiple levels of abstraction, and they create a hierarchy of simple to complex. So this is something that us humans also do. So in a visual cortex, everything is organized, and early areas detect very simple features like edges, colors, basic textures, and then the middle part like detects parts and patterns, which might be in our case eyes, ears, wheels, whisker patterns, eye shapes, etc. And then it comes down to complete object, like combining all of the above to build cat faces, dog bodies, specific poses, etc. So one concrete example might be that the layer 1 might detect edges for cats and then or dogs, and then the fur texture, whisker pattern, and then the eye, ears, eyes, nose shape, and then the complete cat faces. So the classical methods plateau with more data, and deep learning improves with more data and compute, and state of the art results on most vision tasks. So deep learning has more accuracy, as we saw earlier. So there's a rule of thumb as to when to use what. So if we have very small data set, the classical methods run very well, and deep learning can be really risky. It might overfit. So the clear winner in this is classical method. And then if we have large data sets, for example 1 to 10k or okay, so let's talk about medium data set. So if you have a medium data set, then both will perform nicely. So this might have good performance. And if we do transfer learning on it, which will come in the later section of the video, then deep learning will win in this case, but both are pretty decent. And if you have large data set, for example, let's say greater than 10,000 images, then deep learning method is the clear winner here. And then if we have no compute or we don't have unlimited GPU, then classical method wins because it has faster training in minutes, while deep learning might take hours or days on CPU. So the clear winner here will be CPU. And then the same thing with fast inference. It takes milliseconds per image, and it takes slower, but it is still getting optimized in current date. So the classical is the winner here. And the state of the accuracy, obviously deep learning will be the better, because if it has like 75% accuracy, this might have greater than 95% accuracy. So it's a clear winner here. And lastly, I even want to add, if you want interpretability, so in classical you manually handcraft the features, right? So you have complete control over what you built initially. So it might be more interpretable because the features are understandable. But in deep learning, there's a black box, so that can be harder to interpret. So the classical methods will be the winner here. I hope you got an intuition as to how what is the difference between classical methods and deep learning. So let us come to how to code a CNN from Flatware. So let us come now to building CNNs. So so we have CNN building blocks. So firstly, let us import all the libraries. So we'll use PyTorch here. It's a deep learning library. And then let us import PyTorch neural network as a short form NN, and then NN functional as F. I'll tell you what functional is later on in the video. And then let's just import NumPy and Matplotlib. And let's just verify if the libraries has imported successfully. So all the libraries have some imported successfully. If you don't have any library, you can just do pip install torch, um, and then numpy matplotlib accordingly. So let us come to convolution layers. So this is the core part of the CNN. So a convolution layer has some fundamental building blocks. So convolution layer is the heart of CNNs. So it has some learnable filters which are known as kernels. So these filters basically slide across the over the input image, and they perform element-wise multiplication and summation to produce feature maps. So what does this mean? So let me walk you through this step by step. So firstly, we have a filter initialization. So a filter which is actually a small matrix of weights. So we have a matrix full initialized with random weights, and it is applied to specific region of the input image. So our filter in itself will start from a starting of the image, and it will slide across the whole image, and it will perform multiplying matrix multiplication. So our second step will be element wise multiplication. So each element of the filter is multiplied to the corresponding element of the image region. So after you multiply everything, you'll just sum everything over. So the results of these multiplication are summed up to produce a single value in the feature map. So you'll get a single value of the feature map after summing everything over. So this is our third step. And then let me also tell you what stride. So stride. Uh, So sliding the filter actually, when you slide it across the whole map, so there's something known as how many pixels at a time. So this is known as stride itself, and then we have element-wise multiplication, and then we have summation, and then this feature map creation. Uh, So feature map creation is for every position of the filter over the image. It results in a 2D feature map that highlights specific features of the input image, which is produced by summing over the matrix multiplications. And then we can have multiple filters. Uh, we can have multiple filters that can be used to extract different features, resulting in multiple feature maps. So that's how it works. Mathematically, there's a formula for these matrix multiplications. So for input I and kernel filter or kernel k, output feature map O is computed as. So we have a summation over matrix multiplication between the image and the kernel. So I hope you got the intuition behind all of this. So let me just scroll down. So I hope you got the key concept, and the key concept here, it's that a filter or kernel slides across the whole image, and it will perform element-wise multiplication and summation to produce feature map that will highlight specific features of the image. So in using PyTorch, let's see how to define a single convolution layer. So single convolution layer. We'll use NN that we imported from here using in PyTorch library. So to define a convolution layer, we write nn2 uh, nn2 dot con2d, and then we input our parameters. So firstly, we'll input how many channels we have. So if we have a RG image, we'll have 3 channels. And then the next parameter is what our filters would be. So we'll have, if we have 32 filters, so we'll output 32. And then we have to see how many, what is the kernel size. So kernel underscore size, let's do 3 by 3 for now. So 3 into 3 filters. And then how many, what is the movement of our number of pixels at a time. So if our stride is 1, then we'll move 1 pixel at one time. And then let's define padding. I'll come to the output size and padding in the next code cells. So just for demonstration purposes, let's input a batch of RGB image. So in PyTorch, how you define random images is using torch.random, and then the batch size, the channels, and height and width. This is something we saw in the earlier sessions as well, as to how to define random images. The difference here is that you use torch library instead of NumPy, and then you use output, and you input all of our images to our convolution layer. So you input convolution X, and then you can input the shape of the input, so output shape, or you can even do input shape. So input shape is X dot shape. So as you see, input that we just input to our convolution layer is 16 batch of uh 64 images with 3 channels, and then the output is exactly torch size 16 32 64 64. So this was our output size, and then this was input size, and then everything else is same. So the number of images will be same and height and width will be the same. So I hope you understood the meaning behind all of these parameters. Let me just write it for your convenience. So a meaning of parameters. So let me just iterate you through everything. So in channels will be the input channels, which are RGB, and then for grayscale images this would be 1. And then we have out channels, so we have the number of filters that we want to define. So here we have 32 different filters, and then each filter will detect a different pattern. So vertical edges, horizontal edges, etc. This will create a 32 feature maps, because we have 32 out channels. Then we have kernel size, so the common values for this might be 3, 5, 7, etc. So smaller kernels are preferred because they capture local patterns effectively. Because for stride is equals to 1, you'll move across each pixel basically. So you'll move, if you have stride is equals to 1, then you'll move one pixel at one time. So if you had stride is equals to 2, then you would basically skip every other pixel technically. And then if you have padding is equals to 1, to which we are coming later on, then you're adding 1 pixel border of zeros around the image. So for a 3 cross 3 kernel, padding is equals to 1 will, like, if you have a whole input image, then a layer of zeros will cover the whole image as a border. And then this is just okay. So let's just define everything here. So stride is, uh let's go sequence. So in underscore channels, the number of channels, then out of channels is number of filters, then the kernel size, the stride. So these are our input parameters. I hope it's clear. This is done. So let's understand padding. So padding layer. Now the problem is that if we don't define padding, our convolution will shrink the images. The concept of padding is that basically in convolutional neural networks involves adding extra pixels around the border of the input image before applying convolution layer operations. Now let me walk you through as to why the output size will decrease uh, as compared to the input size. So the thing is that when you have a 3x3 filter and for example you have a whole image, right? So in a 3x3 filter it can't be centered on the edge pixels. So if you, for example, if you have this picture that is the table here, so if a 3x3 filter is here, then it can't be centered on the edge pixel here or edge of edge pixel above or edge pixel below. So these edges which might be the leftmost position or the bottommost position, like they'll be left out and we can't actually perform matrix multiplications on it. So if we have like indexes going from 0 to 31, then might be the fact that we'll only get 0 to 29 because our leftmost and rightmost edges were not computed, and same for topmost and bottommost. So there's a shrinkage problem here. And so why does it shrink? It's because of the edge pixels. So when a convolution operation is performed without padding, the size is reduced compared to the input image. This is because it can only be applied where it fully overlaps with the input image. So for edges, it doesn't fully overlap. That's why it shrinks. And then there's types of padding. So types of padding. So we have different types of padding, and one is no padding. So one is no padding. So no pixels are added to the input image, and then the output feature map will be smaller than the input image as described above. And then there's same padding. So here extra pixels are added around the border of the image that the output image has the same spatial dimension as the input image. So the amount of padding depends on the size of the filter size and stride in the convolution operation. So for example, in this case, if your stride is equals to 1, so if we are moving 1 pixel at a time, then a padding of 1 will be sufficient to define the same output size as the input size. But if you have stride is equals to 2 and you're leaving each pixel, and if you like, it depends on your dimensions of the image itself. So you might leave the topmost and the rightmost pixels. So in that case, you might want to define padding is equals to 2 for taking care of the same thing. And then there's something known as full padding. So it involves adding enough padding so that the filter can be applied to every possible position. So padding that might be greater than 1. So I hope you understood what padding is. Let's just come downwards. Right. So let's see how to code it. So we have x is equals to torch.random. Okay, so we have torch.random, and then let's just define a single grayscale image, or let's do better, let's just do with RGB image itself. So we define one image and then we have RGB image, right? So we have RGB image of size 32 into 32, and then let's just see the results with no padding. No padding. So convolution no padding will simply be padding is equals to 0, and then we have output image will be, which will be convolution layer giving x as input. And then let's see with padding. So with padding our parameter will change to 1 here. So as we saw, if we input a 32 cross 32 image, then without padding we got our dimensions reduced to 30 into 30, and if we use padding we get an image 32 into 32 because we got borders of zeros, and then even our edges were conserved in that case. That's it for padding. I hope it's understood. Let's come to something known as output size calculation. So output size calculation. So being able to calculate output dimensions is crucial for designing CNNs because you need to know the size of feature maps at each layer to properly connect them and allocate memory. So because in your whole architecture you'll have different type of convolution layers and you need to connect all of them, so you need to calculate output by some metric before using the actual network yourself. So there's a universal formula for that, which will be w minus k plus 2p upon s plus 1. So here w is our input size and then k is our kernel size, and then padding is basically the amount of padding you do, and you divide the whole thing by the stride, so the number of pixels we move, and then you add 1 to it. So as I told earlier, so this is basically all the key components. So let's just see how to actually use this formula. We saw this formula right now, right? So input size minus kernel size plus 2 into padding by stride plus 1. Now let's verify it using actual convolution layer and let's see if our formula is working. So we have some test cases. So let's define a list with random examples. So we have these examples. So in this case we have 0 padding. In these cases we have 1, 2 padding, and then this case we have stride is equals to 2. So let's just define. So for each input size, kernel size, padding and stride in our test cases, let's use this formula. So we'll use output size and then we'll input all of these values in our defined calculate function. So this is what we have calculated. So calculated output size and then see what the actual output size is. So let's just verify with actual convolution. So we have random images, so torch.random n with these parameters. So we input the input size and the input size as height and width, and then we define a convolution layer with our defined parameters here. So so we have a kernel size as kernel size, stride as stride, padding as padding, and let's output convex as inputting all of these input images into our convolution layer, and let's just output the shape of our like define output from convolution as output.shape2, and let's see if our formula is getting verified here. So as you saw, so so if you input size of 32, then your kernel size uh, and for kernel size 3, padding 0, stride 1, you get output size of 30, and then from our formula itself, as you saw here, so so the first print statement in itself will output all of the parameters. So we got output size from our calculate output size function as 30, and then our verified output shape from nn dot convolution 2d is 30 into 30. So as you see, 30 is here and then 30 is here, so our output size is getting verified. So same with this, same with this. So as we saw for all our examples, this formula is actually replacing the using convolution x and then outputting the shape of it. It's very useful in terms of times when you need it for defining different convolution layers. So you need to know the output size of each convolution layer. So I think convolution layer size is clear. Okay, so now let's come to activation functions. So what are actually activation functions? So activation functions are actually to introduce non-linearity. So they actually help the neural networks to learn complex patterns. So they introduce non-linearity to the neural network and it allows it to learn complex patterns. Um, so let's just say that without them, So we'll have multiple linear layers stacked over, and it would behave like a single neural network. So you guys might have studied in your JEE or some maths course that if you keep inputting linear function as the next function, so if you have y is equals to mx plus c and x is a linear function, so you'll get y is equals to some different linear function, but it will still remain linear. So that's how we need to create some non-linearity so that our neural network is not just some one linear function. So some common activation functions include ReLU, which is short form for rectified linear unit, and then we have Sigmoid and Tanh. So let's come to ReLU. So ReLU. So ReLU has a simple formula of maximum of 0 comma x. So it simply replaces all the negative values with 0. So let's just see how the code of it works. So we have ReLU. So we'll use the inbuilt PyTorch function for ReLU function, which is nn.ReLU. So let's just define ReLU as nn.ReLU. So in PyTorch library itself, we have a function inside neural network. So we imported PyTorch neural network as nn. So nn.ReLU has a ReLU function. You can even define a function for it if you want. Let's come to it later. Let's just define a tensor for outputting our ReLU function. So if we input a tensor -1, 2, 3, -4 to our ReLU function, we'll get something like 0, 2, 3, 0. So all the negative values actually converted to 0. So that's the key purpose of ReLU. That's how ReLU works. And what I was telling earlier about creating a manual ReLU function. So we'll just use torch.maximum or np.max like in first lectures. So you'll use the maximum value of torch tensor 0, 0. So you have 0, 0 tensor, or you just input x value. So this is how you can even create your manual ReLU x, or you can just simply use nn.ReLU. And then similarly for Sigmoid and Tanh. So the sigmoid function's formula is 1 upon 1 plus e to the power minus x, and then tanh formula is e to the power x plus e to the power minus x upon e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. So these are the two formulas for sigmoid and tanh. And in similar fashion, as you use nn.ReLU, you can use nn.sigmoid or nn.tanh. So some other activation functions. So you have tanh is equals to nn.tanh, or sigmoid is equals to nn.sigmoid, and then you can define a tensor, and our tanh output will be tanh x and sigmoid x. So if we had -1, 1, 2, so as you can see in tanh we applied tanh function which we defined here, and we output sigmoid as well. A key observation here is that sigmoid always gives positive values, because at negative infinity, sigmoid will give 0, while at positive infinity, it will give infinite. But in tanh, you get a minus infinite to infinite curve. So in that case, you'll get, no, in tanh, you'll get -1 to 1. So maximum you can get uh, 1, minimum you can get -1, but in sigmoid you can get 0 to 1. So at negative infinity you'll get this whole output as 0, but at positive infinity you'll get this as 1. So minimum is 0, maximum is 1. So this is how sigmoid and tanh works. So next we have some pooling layers. So pooling layers. So the pooling layers are basically to save some computation. So these are basically downsampling the feature maps. So pooling reduces the spatial dimensions of the feature maps while retaining the important information. So if we have a lot of images and we want to downsample them for saving our computation, so we'll reduce the number of parameters and computation in the network. So it can even help in controlling overfitting, because you're only keeping the important parts of the features and reducing a bunch of them. So let's just depend benefit of. So firstly, our dimension will reduce. So normally if you pool, so if you use maximum pooling or average pooling, so if you have a 64 network, uh, if you have a 64,64 image and you use some type of pooling like average pooling or maximum pooling, your dimension will reduce from 64 into 64 to 32 into 32. So you save 75% of your values. So it will decrease the number of parameters. So it will help in training and inference. And then you have something known as translation invariance. So it's just like if you have at an edge for example at 10 comma 10 or 11 comma 10. So if you use maximum pooling, which we'll be seeing just right now. So in maximum pooling, it will capture the same strong signal. So it will make the feature more robust to small shifts. So it will not focus much on small shifts. So more robust to the small translations or shifts to the input image. This is because if you use maximum ReLU, so it will just give one value out of two of 10 comma 10 or 11 comma 10. So you'll get the same value and it will become more robust to small translations. And then it will even help in controlling overfitting. So if we reduce the spatial dimensions in deep learning methods when networks with many layers, it can help in overfitting as well. Now let's see how to define maximum pooling and average pooling. So something known as a window. So your window can be some depending on the kernel size itself. So maximum pooling in itself is defined as nn dot max pool 2D. So you input your kernel size and with which stride you want your kernel size to move. So let's define our x as this. So for demonstration purposes, we have 1 to 16 here as our tensors, and let's just see how our input and output changes. So before outputting, let me explain you as to how maximum pooling of 2D works. So if your window is here, for example, so if your 2 comma 2 kernel is here, right? So in this window itself, your maximum pool will be operated and you will get your maximum value. So in this specific window, the maximum value is 6. So out of 1, 2, 5 and 6, we'll keep the 6 value to represent this entire window. And as we have side is equals to 2, instead of moving here, we'll move here. So we shifted from one window to another window. And as we can see in 3, 4, 7, 8, the maximum value is 8. So we'll keep 8 from here. Similarly, we'll keep 14 and 16 from here. So as you saw, we kept the maximum values in each window. If we had side is equals to 1, so we would keep maximum values from each side. So from each window, our window will be here and here. So we would have reduced from 4 into 4 to 3 into 3. But for side is equals to 2, we'll reduce from 4 into 4 to 2 into 2. And then you can even do the same with mean pooling. So mean pooling is like taking average value in each window. So you define average pooling or mean pooling as n dot average pooling 2D, and same as above, but in this case it will take the mean of each of these values. So earlier it was 6 because it was maximum pooling, but here it will be the mean of all these values in the window. So this will be 3 plus 6 9 plus 5 14 by 4, which is 3.5. So you would get, so we'll get 3.5 here, and then for this window you'll get the mean of all these values. So you'll get 5.5 here, 11.5 and 13.5 respectively. So you'll basically get the mean here instead of the maximum itself, and that's how you perform pooling. So I hope you got the intuition of all these key components. So we started by convolution layer, and then we defined banding, and then we saw how to see output size calculation using a defined formula, and then we had activation functions. And then we saw what is pooling. So it's to reduce dimensionality to save a lot of compute. Now let's see how to combine all of these for a complete CNN architecture. So firstly, a complete CNN architecture will consist of multiple convolution layers followed by activation, and then we'll pool it. After such several layers, the feature map is flattened into 1D vector and passed through a fully connected layer for regression or classification tasks. And the final layer uses the softmax activation function for multi-class classification problems. So firstly let me tell you what is a fully connected layer. So a fully connected layer is a layer in which each neuron is connected to one neuron in the previous layer. This layer is typically used at the end of the CNN to perform classification based on the extracted features by convolution and pooling layers. So fully connected layer is basically something that comes after the convolution layers and the pooling layers, and after that you get the features extracted from the convolution and the pooling layers. Fully connected layers will use those features to actually perform classification tasks. So it's basically in machine learning you might have studied what w dot x plus b means. So y is equals to softmax into w plus x plus b. So you perform dot product here, so you can say x into wt. So if you have w transpose, so this is how you define y function here. So in fully connected layer you can have linear or softmax here depending on the type of activation you want, and then you do compute here with respect to what features you got from the earlier layers to a matrix, and then you add some bias to it, and then you do softmax or linear here. So that's how you define your fully connected layer. And now let me just show you how to code this along. So it's pretty simple. You define a class known as simple.cnn. In simple CNN class, let's define our init function first. So we define our simple CNN and self, and inside that let's define our convolution layers. Okay, wait, let's just define super here. So our convolution layers. So our first convolution layer, let's define as input channels as 3, output channels as 32 or 16, same thing. So 32. And then second convolution layer, so the output of this should be the input of the next convolution layer. And similarly, let's define the third convolution layer. So input will be 64 and then we want a 128. I think 3 convolution layers should be enough, and then we define pooling here. So pooling layers. So self.pool is equals to, we'll use max pooling here with kernel size as 2 and stride as 2, and then we define fully connected layers. So we have 2 linear fully connected layers. Input size of 1 will be 128 4 into 4 vector, and then we have output as 256, and the input for the next fully connected layer will be the output of the first connected layer, and this will be the number of classifications that we need to perform. After this, okay, so let's define our forward function. So there's a full hierarchy that we need to follow. So block 1. So firstly we need to perform convolution, then we need to apply our activation function on it, and then we define pooling. So this is how we perform the block 1 operation. So we firstly perform convolution, and then we pass the output to ReLU function, and then we use pooling. If you are wondering what is f, so f is a function inside library of neural network in PyTorch that we put a short form for functional. So torch.nn.functional, It's the same purpose that we used as n.ReLU. So if you don't want to use f, you can define self.ReLU here. So self.ReLU is equals to n.ReLU, and then instead of f here you can use self.ReLU. It's completely up to you, but let's use f here. You can try it on your own, it's the same thing. And then similarly for block 2 and block 3 we have the same compute. After we define our blocks, let's just flatten it. So one thing that you should need to know about fully connected layer is that it takes an input as a 1D vector. So for inputting to a fully connected layers, we should firstly flatten our output. So we can use x.view here. In first few sessions we saw np.flatten, and we can use x.view here similarly to output 120 into 4 into 4. And now we use our fully connected layers. So our fully connected layer will be so firstly we pass self.fc1. So we input our linear fully connected layers, and then we pass ReLU to it. And let's keep the second as let's keep the second fully connected layer to not pass to softmax for now. We can use it while training directly. So let's just output raw scores, and then let's try to instantiate the model. So we call the model using simple CNN, and let's define some random images. So x is equals to torch.random. So we have a batch of 16 images, each 32 into 32 with 3 channels, and we define our output as inputting x images into our model. And then let's just see the model output. As you saw, we should get 10 classes here. So for each of our 16 images, we got it got classified into one of the 10 images. So that's how our complete CNN works. So in our CNN building blocks, the first thing that was there was the convolution layers, and then we understood padding, then the pooling, what is pooling, and then even activation functions, and this was the output size calculation. So if you define padding correctly, you'll get these outputs. And then the next thing is how to train a CNN on a CIFAR10 dataset. So that's the next thing that we'll do. So let us now see how to train a CNN model on a specific dataset. So let's just give it a heading. So firstly, let's see if our imports are working. So import torch as nn, and then we have let me think what our libraries will need. So we'll need torch neural network, and then we need optimization. So we can import torch.optim as optim, and then we'll even need functional. So import torch.nn.functional as f, and then we'll need torch vision for datasets. So from torch vision, let's import datasets and transforms, and then we'll need torch dataset loader, and I think that's all. So import numpy as np, matplotlib as plt, and let's see if it's a okay. Let's just import these for now. So we have all of these imported. Now the next step that you need to see before training your own CNN model is if you are using GPU or not, because you should use such big computations such as neural networks on GPU itself, because on CPU it's very slow. So how you can do is using torch.device. So let's define a device. So our device is torch.device. So CUDA if torch.CUDA is available. Yeah, so we have defined a device as CUDA if torch.CUDA is available, as in if your laptop has a GPU, else it will work on CPU. So if you're using Kaggle or Colab, for example, you can see if your GPU is activated using this function. And when we output this, it outputs CUDA. So this means our GPU is working. So now let's come to defining a CIFAR10 dataset. So let's prepare a CIFAR10 dataset. So CIFAR10 dataset is basically a dataset with 60,000 images that are classified into 10 images, 10 classes. So CIFAR10. So it's a widely used dataset for training machine learning and computer vision models. It consists of 60,000 32 to 32 color images in 10 different classes with 6,000 image examples per class. And the dataset in itself is divided into 50,000 training images and 10,000 test images. So that's how CIFAR10 dataset works. So firstly, let's do some data pre-processing. So we define transform as transforms.compose, and then this is how you use transformations in PyTorch. So let's let for your purpose, let me just write it here what it is actually doing. So let's define a pre-processing. So the below code actually performs. So it defines pre-processing transformations to tensor plus normalization. So we'll just keep updating it as we go along the code. So when we use transforms.compose and then we input in some parameters, so it will chain multiple transformers into one. So let me just write it here. So transforms.compose chains multiple transforms into one, and then we have transforms.toTensor. So transforms.toTensor converts images into PyTorch tensor. So it might convert a PIL image or ND array to PyTorch, and then it will even scale it to one. So PyTorch tensors is basically that you have some channels height and width, and each pixel value will get scaled to 0, 1 if you don't know what PyTorch tensor means. And then we have transforms.toNormalize. So transforms.toNormalize extracts mean and standard deviation, and then it normalizes each channel by doing x minus mean upon standard deviation, as we saw in the second second video itself. And then we load our data set. So we define train data set. So we use datasets.cifar10 and then we pass it our root. So root train is equals to true, so we'll get a training data set. Download is equals to true, and then we'll apply transformations. So what it does is that it loads in so download and load the CIFAR10 dataset and the test dataset. So it will basically load the CIFAR10 dataset, and if it will download if it's needed, in this case it's true, and then it will apply the transform to each section. Well, let's do the same for test dataset, and now let's just print it. So So we loaded our data set. Now we need to create some data loaders. So create data loaders. So what loaders does is that let me just write it here. So our pipeline will wrap the data set in data loaders for batching and shuffling. Okay, so our data loaders is basically it like we got training and the test data set here, and the data loader in itself it creates an iteration. So over the data set it will create mini batches of your training data set for further training. So we define data loader and we give it a trained data set and the batch size that we need to iterate our training over, and then we shuffle it. So if you want to shuffle it, it depends on you, and then you can even print if you want. So training samples. So it will take some time, but our training and test samples are 50,010, and then we have some classes in a SIFT 10 dataset. So these are the 10 classes that the dataset is made onto. So we have plane, car, bird, cat, deer, dog, frog, horse, ship, and truck. So these are some classes that the model is classified into. So let's visualize some examples. So let's create a define show images. So we input our images and labels, and then can even input our classes. So firstly, for Matplotlib pre-processing, you need to unnormalize your image. So how it works is that you firstly normalize your image for loading in the dataset, but for Matplotlib for loading itself, you need to remember that you need to unnormalize your dataset images so that you can plot it. Let's just see if it worked. So let's just iterate the dataset data iteration. So we iterate over a training loader, so batch size and everything, and then we use images comma labels is equals to data iteration dot next, and then show images. Okay, I didn't input anything. So okay, I input the wrong function. So next data iteration. So this is some examples we have. So for cat we have these images. For truck we have this. So these are the different type of images we have in a data set. So it will create an iterator object from the data loader, which basically iterates over the batches in the defined function, and then next data iteration will get the next batch of images and labels. In this case, it retrieves the batches of the corresponding labels. So that's what it does, and then show images basically matplotlib function. So we got different type of batches, so different type of images here, and then let's define a CNN model here. So firstly you retrieve the data set, and now you need to define your CNN model. So same as we did for a simple CNN class here, we need to do the exact same thing. So we have class CFAR 10 CNN, and the same thing that we did above, the exact same thing. And let's just define a model here. So model is equals to, and then print model, and we can even visualize the total parameters here. So let's do /n here. So this is our model configuration, and then these are the total number of parameters in our model. Okay, so now let me tell you something known as a sanity check. Sanity check. Overfitting on one batch. So now we have our model defined and our data set defined. But the thing is, we don't know if this configuration is the best for our data set. Might be that we never get good results, and if we train it for a lot of epochs or steps, we are just wasting our computation. So there's something known as overfitting on one batch. So before training your model on the full data set, verify if the model can learn by overfitting on one batch. So it will just see if the model architecture is correct and if the loss function and everything works. So before training on the entire data set, so this will test. So model architecture, our loss function, optimization process, and I think yeah, this is fine. So let's take in the batch of one of our images. So take one batch. As we used earlier, so we'll use train loader iteration. So train underscore images or wait, test underscore images. So we'll use train loader to import some test images for overfitting our data, and then let's define. And let's define firstly you loaded your image using train loader and you got one batch, and then you use images.to device. So you loaded your tensors to your device, so whatever device you're using. So we defined our device as CUDA here. So we defined a device as CUDA here, and then we just load all of our tensors that we defined in this one batch to our device, which is CUDA here, as I told earlier. So sanity model will be our original model that is loaded on the device, and then we will define some criteria. Let's just use cross entropy loss here, and when we have some optimizer, so self underscore model dot parameters, and then we have a learning rate. So this will create sanity model, and then this is a type of classification loss. So for you have different type of metrics for regression and classification. So cross entropy loss is a classification loss for logits plus integer labels. You can use any metric here as long as it's sensibly correct. And then this is just Adam optimizer. So this is a type of optimizer that we use in deep learning. If you are interested in knowing about more optimizers, you can for sure look up for it, but I'm just gonna define optimizer for now. And then our main goal for here is that our loss should converge to 0. So our loss should significantly decrease over a few epochs. If loss does not increase, it may indicate that there's some issue with the model architecture. Final loss should be close to 0. So we define our model criteria and optimizer. So for 100
or let's just say 20 epochs. Let's define optimizer.0grad, or okay, let me just type it all so that it's easier for you to follow. So we have outputs. So let's pass in a test images to our model, and then we define cross entropy loss for outputs and test labels that is predicted, and then we define optimizer.grad. So optimizer.0grad. So what it will do, it will clear the old gradients. So the optimizer will clear the gradients, and then loss.backward will create new gradients via backpropagation. So it will create backpropagation, and then we have optimizer.step, which will update the weights aka parameters. So basically we created our loss function through the model itself, and then we had loss.backward, which will compute the gradients via backpropagation, and then we are updating our weights using optimizer.step, and then we'll print our loss function. So we can do that by I percentage 20 is equal to 0, or let's do that for every 5 epochs. So for every 5 epoch, let's do loss.item, which will print our loss itself, and then we can print our final loss using loss.item finally. So as we saw, so we trained our model for 20 epochs. Let's do for 100, so we can see what I actually meant. So as we saw, for 100 epochs, our loss significantly decreased over 100 epochs, so it became very close to 1, very close to 0. And if we output it for every 5 epochs, as you saw, so the loss significantly decreased from 0 to 5, 5 to 10. Can we input, and then we have it decreasing over multiple iterations, coming close to 35. It became very close to 0, and it just converts to 0 henceforth. So as we saw on our one batch of images, our model itself converts to 0 loss. That gives us an idea that a model is good enough for our training, and then we can fix any issues that come along the way. But for initial training, it's pretty good and everything is working correctly. So let's define a training loop. So our training loop will be exactly same as our overfitting batch model. So whatever I explained here, I don't think we need to go through it again. It's just that you'll just pass in training images instead of overfitting. So our training loop. So training the model on the full data set. So let's define a model, criteria, optimizer, and then let's define our configuration here. So number of epochs 10, and then train loss and test losses as empty lists, train accuracies. So for epoch, range number of epoch, so we use model.train, and then our losses are 0 here, and then for each image and labels in the train loader, we use images.to as we saw earlier, and then we output our image using model images. So we forward pass, we get some loss, and then we back propagate using whatever we learned in the overfitting batch cell. So our running loss will be simply addition of loss.item into image size of 0, or we can even skip this if you want. So simply it's loss item, and then our images will be torch.max, predict, so our predicted, so see, the thing is underscore comma predicted will get us our predicted classes from logits. So we use dot data to access the tensor. So outputs dot data, and then we use the maximum value from either torch.data comma 1, because our predicted can be 0 or 1. So this is how it works. And then our total will be labels.size 0. So how many labels we have, it gets keeps added. And then our correct label would be simply predicted is equals to labels dot sum dot item. And then we can even print like we did in overfitting batch. So if I plus 1 percentage 100 is equal to 0, let's just print our number of epochs, like batch and loss, what loss we are getting for each batch. And then we have a total epoch loss, running loss upon length of training load dataset. So our running loss by the number of training examples, and our accuracy will be correct upon total into 100. And let's just append our epoch loss into this list. So let's just run it now. So our model is getting trained on a CFAR10 dataset. So this will take some time, but eventually we'll get a trained model whose loss will be quite low, and it can predict our images into some one of the 10 classes. And while this is printing, let me show you how to actually evaluate on a test dataset. So let's just come here. So evaluation. So it's the same thing as above. So you define, as you define model.train here, let's define model.eval. So model.eval. So just like you did for this training loop, so you have correct as 0. So correct as 0, total as 0, and then for test images, let's even define what is class correct. So you have class correct and class total. So it will create a list. So the number of classes you have for output, it will create the list of same size. So it will create a 10 element list with zeros initialized. So for each correct class that we get from our model, we'll increase the value of that specific column by 1, and we'll do the same for total. So it's the same thing as above. From test loader, we load some images and labels, and then we load them to our device using .2, and then we'll output our images, and our predicted will be just getting the output and toss.max. So the maximum value can be 1 itself, and then our total will be adding all the label size, and then the correct will be getting predicted is equals to label. So if a predicted image is equals to the actual classification, so if we got cat as the model output and cat was the actual image output, like the, for example, in this image, if we got the model output as cat but it was actually dog, so predicted is not equals to the actual label. This is a label, and the predicted will be the model output when we pass our input image. So if predicted is equals to output, then we'll get the correct output, and then we'll store it in the number of correct items. And then this is just to add per class accuracy. So So this is per class accuracy. So you'll see if your predicted labels, like as I told earlier, if your predicted label is equals to, if your predicted class is equals to the labeled class, then you'll put it in correct, and then you'll just add labels etc. to it, and then your final test accuracy will be 100 into correct by total, and then you'll see the final test accuracy, and then you can even see per class accuracy. So per class accuracy, so you'll just iterate over each class, And then if you have class underscore total is greater than 0, so if you have some examples in your test images for a specific class, then you'll just find the accuracy for it. Or if you don't have it, so instead of doing 0 by 0, we'll just define that we don't have any samples. So that's how the test inference works. We'll just wait for our model to run. I don't know how long will it take. It usually should take like 3 minutes or something, but okay, let's wait. Okay, we got 9th epoch, I guess, so it will still take a bit of time. It's come to how to visualize our test images. So it's just plotting them on matplotlib. So the same process as above. So we have, okay, this is not coding. So next, so we'll make some predictions. It will be output is equals to model images, and then we'll use torch.max, and then we'll show the results. So let's create a function. Okay, sure. So firstly, we'll unnormalize our image, and then we'll load our image to CPU. Like for this, you don't need GPU, but you can use .device here as well, and then you can use matplotlib to visualize all the examples that we saw earlier. So okay, our model is trained. So we got our final training accuracy as 95% and our loss is 0.024%. So let's evaluate our model on our test images. So we got these accuracies. So final accuracy is 77% on 10,000 images. So we got pretty good accuracies for plane, car, and then truck and frog. But as you saw, we got a very bad accuracy for cat. So this means that our defined model is not very good for test images on cat, because these images might not be very good visualizations. So the best class that we got is car. So we can use this to classify car in real life cases. And let's just visualize some of the examples. So these are some visualizations. So our true class was cat, and then it was predicted as cat, and our true class was ship, and it was predicted as ship. Because our accuracy is very good, we'll get good results most of the time. But in this case, it predicted it as cat, but it was actually a frog. As a human itself, you can get pretty confused because it looks like a cat to us also, but that's how the images in the dataset are. And then you have frog predicting as bird itself, and then one can even confuse this as bird itself, like a sparrow or something. Is it a sparrow? Like any bird of green color, but it's actually a frog. So even humans can get confused in such type of images. It's not the model's fault, but we know now that it's pretty good for some type of classes, as we got in class accuracies, and that's how you train your CNN on SIFT. So this is pretty basic, but like whatever I wrote here, but I explained it in pretty depth here. And the last thing that's remaining is transfer learning. So now let's come to something known as ResNet, which is a famous CNN architecture. So let's just write it here so that you have an idea what's going on. So the thing is, if you take a 20 layer CNN network and make it 56 layers, you think that it would perform better, or at least the same. Let me just come to PDF. So if you have a 20 layer network and you have 88% accuracy, you think that adding more layers will just help it represent more complex functions, or at least it should match or beat the 20 layer network rate. But the accuracy often gets worse as depth increases, and this is not just because of overfitting. So this is known as a degradation problem. So it will actually perform worse than the shallower one. So this is known as the degradation problem, where adding more layers leads to higher training error. So let's come to this part later. So it is not just overfitting, but it is about the model being too hard to optimize. So the problem is that it's not because your model is like very powerful or uh, like overfitting because it's very powerful, but it's mostly because it's getting problems in getting optimized and being optimized and getting trained effectively, because there are two problems that so the degradation problem has mainly two problems. So firstly, it's something known as vanishing gradients. So yeah, so vanishing. So in very deep networks, gradients can become very small or extremely large during backpropagation. So see, in a neural network, right? So in a neural network during backpropagation, gradients are repeatedly multiplied by derivatives uh, over each layer. So in each layer, that can be less than 1. So if those multipliers are less than 1, so the gradients can shrink exponentially, which will just make them vanish, or they can be greater than 1, which can make them explode during backpropagation. So this type of multiplication makes it difficult for the network to learn effectively, as the weights in earlier layers receive very small updates. And the second problem is the identity matrix mapping problem. So in deep networks, it can be challenging for the model to learn effective mappings when needed. This is see, the thing is, in deeper layers, right? So if you have a 20 layer network versus a 56 layer network, so if you tell the model that okay, yeah, if between 20 and 56 layers, the 36 layers are not doing anything, at least what you can do is pass in the input and give it as output. So you want identity mapping, that okay, if you can't decrease accuracy, at least not decrease it. So after all the 20 layers, just pass in my input as output, and even if those layers aren't needed, the best you can do is run an identity function on the extra layers and pass in my input as output, right? But the problem is that in like a plain stack of convolution layers, learning just pass the input through unchanged is like a very a nonsense thing, and it's not very automatically easy to implement such a thing. So the optimization actually struggles to do to find a do nothing solution. So what I can add, this can hinder the learning process, as the network might struggle to retain important information from earlier networks. So So you can the best the model can do in this scenario is learn identity mapping for the extra layers, effectively skipping them. But traditional deep networks struggle to learn such identity mapping, and that's the issue with the second issue with them. So this is where ResNet's ingenious comes in. So what ResNet does is that it learns a residual instead of the full mapping. So instead of forcing layers to learn a direct mapping, what it does is that there's a direct output. So there's something known as skip connections. So instead of forcing So instead of hoping that the stacked layers will learn the desired underlying mapping by itself, so ResNet introduces skip connections or residual connections that allow the input to bypass one or more layers and will be directly added to the output. So what it does is that it learns the mapping, which is known as FX. So FX might be, for example, the convolution So it it helps in two main ways. So see, firstly, it helps by easier optimization. So when you have once again when you have hx is equals to fx plus x, so if you calculate dh dh by dx, you'll get dfx plus dfx plus by dx plus 1, right? So even if your gradients are very small, that is close to 1, you'll get at least 1 as dhx by dx. So So you'll get dhx is equals to dfx plus x, and this will be simply dfx by dx plus 1. So how this matters is that if you have very small gradients for dfx, so if dfx by dx is actually close to 0, then you have this 1 over here, which will let the gradients flow through. So it's very easy for optimization. So, for example, as we saw, one of the issues was vanishing gradients. So, if your gradients are very close to 0, it would cause problems in the network itself, and it will like have it issues to learn effectively. But if your dfx is 0 here, dhx will still be 1, and your gradients will flow through this one factor, which will make it easier to optimize. And then it's like learning residuals. The second thing is learning residuals. So let's come back to here. So if your hx is equal to fx plus x, and your fx is very close to 0, so in your like for example in the layers that are after 20, so in the 36 layers, you want to tell your network that okay, if your fx is very close to 0, so instead of doing anything to fx, let's just define x. So if your fx is very close to 0 in your very complex layers, your y will be just calculated through x, so your y will be equal to x, and y will simply just depend on x, and it will be a linear layer. So that type of layer is known as identity mapping. So by reformulating the learning task to focus on the residuals, so here y will be simply equals to fx plus x, and if fx is close to 0, then y will be x, which is the identity mapping. I hope you got the key points of this residual connection. Firstly, it's easier to optimize, because if your dfx by dx is close to 0, that is the vanishing gradients problem. It will just solve it by passing the gradients to the one factor here, and your gradients will just still flow through. And second is learning residuals. So if your fx is very close to 0, in the complex layers, they'll just learn that okay, I can just pass y through x, and it will just learn identity mapping that we initially wanted but couldn't achieve. So these are two key innovations that ResNet provides. And after that, there's something, so ResNet with 18 layers, ResNet-18, ResNet-50, and then we have some more model, MobileNet, EfficientNet, B0, and they have their own key points as to which to use when. So if you want the best accuracy, then use ResNet-50 and EfficientNet, and for mobile deployment, use MobileNet, etc. So the main purpose of what we do by ResNet is that now you can actually define very complex layers that are like you can define ResNet 50, for example, and because of the two problems that we solved here of learning residuals and easier optimization, you can have very complex layers and not worry about vanishing gradients, and by that you can define complex layers, and it will still work. Now let's come to something known as transfer learning. So see, transfer learning is very logical. So it uses pre-trained models as starting points, and it will reduce training time and data requirements by a whole bunch of things. So see, the thing is, in the earlier layers of each CNN, it learns very generic features like edges, textures, which might be useful for all kind of images. And what you can do is transfer the learning from these earlier layers from a pre-trained CNN and only train the final layers that you want to do for a specific purpose, and it will still have stay the same state to art accuracy, and this will decrease the amount of data that you need and the training time that you need by a whole bunch. And how it works is that in the initial layers it will learn very generic features which are edges, textures, which are useful for all kind of images. And we can only and what we do is that we use these and we only retrain final layers for a specific task. And what it will do is require much less data, and it will take very less training time instead. So let's come to this. So as usual, let's import all our libraries again. So let me just write it here. So it leverages the fact. So whatever I told earlier. So import torch. We actually don't need the data loader here. Let's just even remove data sets here. And then matplotlib. And then we can check our device. So we're using CUDA here, as we know. So hmm. So early layers of CNN learn generic features and that are applicable to many tasks, while the later layers learns task-specific features. So by using a pre-trained model, you can leverage these general features and adapt them to your specific task with less data and training time. So only the final layers will learn task-specific features. So you'll use a one second. So you'll use a pre-trained model. Use a model pre-trained on ImageNet, which which have learned generic features, and then we'll freeze these early layers to retrain general features, and then we'll train only the final layers. So let me even write when to use. So when you have limited amount of labeled data, or when you're training a deep model from scratch, it will be very time consuming. So many these. So firstly, let's proceed by loading up pre-trained ResNet. So you use model.resnet18. Pre-trained is equals to true. So you load a pre-trained model, and then you can print the model if you want. So print the model, and then you can even input final layer input features, final layer output features. So print f slash in input layer output features, final layer input features, model.fc.in features, and then you can even do it for output. So output features. So this is your configuration. So you have convolution, batch normalization, ReLU, max pooling, and then you have a sequential block using convolution, batch normalization, ReLU, convolution 2, batch normalization 2, and you have a basic block 2, for example. So this is how a ResNet-18 works. And then final layer input features is 512 and the output features is 1000. So as I told you earlier about the basic ResNet architecture. So ResNet's innovation, skip connections, what I told you earlier. So input X. So it will pass through convolution layers, ReLU pooling, and then you have fx, and then it gets added to x, and then you get an output y. So it will just work by uh, so let's use model.named underscore children. So let's print the ResNet-18 structure. We can do that by uh, using name comma layer, and then uh, let's print residual blocks in layer 1. So print, so we have a residual block example. So for I in block in enumerate model layer 1. So this is how it works. So this is the ResNet-18 structure. So you define the name and the model itself. So convolution one, whatever we saw earlier, and then in the end we can even see what. Wait, let's just comment this out for now. So you have all of this, and then you can even see it for layer one. So ReLU, convolution, and then batch normalization. So this is how ResNet-18 is. So let's come down to freezing the pre-trained layers. So let's freeze all the layers. So let's do by for param. So in the model parameters, let's define parameters. Let's just define that our parameters will not require gradient. So let's do param dot requires gradient is equals to false. So it will freeze all the initial layers and then replace the final fully corrected layer. So model dot fc is equals to nn dot linear. So we are assuming that we need uh like we want 10 classes for CFAR 10 in our ResNet-18 structure. So in this, let's do model is equals to model2 dot device. And let's define our countable trainable parameters. So there'll be only some trainable parameters, and that is only for a final connected layer. We don't need it for the initial layers. So let's see what the total parameters are and what is the trainable parameters. So our total parameters is sum of uh, so p dot numel for p model dot parameters and trainable is just like if p requires gradient. And then let's just do some print statements. So as you can see, in such a big model with like 1, 2, 3, uh, yeah, it's a very big model, right? In this, the only trainable parameters, which is the last layer, is only 5130. So as you can see, you saved so much of your time, and in such a good model like ResNet-18, you can use it for a specific purpose. That was to like classify it into 10 classes, which were in the CFAR 10 dataset. So that's how you do it. And now let's set up the training setup. It's just the same as we defined it for our own CNN model. The only new thing here is how to freeze the initial layers and how to define the last layer, and then define a training setup. So let's just only optimize parameters of final layer. So let's define a criterion as cross entropy loss. So n dot cross entropy loss, and optimizer as Adam optimizer as we were using earlier. So print optimizer. So we have this optimizer group with learning rate as defined, etc. And then we have learning rate scheduling. So there's something known as learning rate scheduling as well. So see, the thing is, if you are in a real life training of neural network, the loss should decrease, but the learning rate should also decrease over time so that the convergence is better. So this is the whole theoretical part of learning rate, that the learning rate should also decrease over time for better convergence. You can look up for it if you want, but trust me for now that this happens. So this is something known as learning rate scheduling. So you don't need to focus much on it now, but you just need to know that these things exist. So there's something in step LR. So there's something in step LR. So it will decay the learning rate of each parameter group by gamma by each step size epoch. So you define the step size epochs for which your learning rate will decrease, and for that many epochs the learning rate will just decrease. So you can just do, you can either import step LR, or what you can do is use step LR and then you pass in our optimizer and then you pass step size. So after every 7 epochs, you need to reduce your decay the learning rate by gamma. So that's how it works. So it's a fixed method of reducing learning rate. And then second is reduce. So it will reduce learning rate when a metric has stopped improving. So this is a type of learning rate scheduling that we use the most. So for example, if your loss is not decreasing, and like if your loss is like 0.02, 0.01, for example, that then the learning rate will itself decrease. But if the loss is like decreasing very nicely, like for this example, the loss was decreasing nicely. So till here we got like 0.07 to 0.04. So it's good convergence. But if we don't get that type of convergence and our loss is like pretty saturated, it will decrease the learning rate by itself. So just like above, from torch.optimization, learning rate scheduling, you can even import reduce LR on plateau, and you can use scheduler plateau is equals to like same size above. So you use mode is equals to min factor is equals to 0.1, by which factor you want to decrease, and what is the patience of the metric used. So that is how it works. And then we have cosine angle LR. So it will set the learning rate of each parameter using a cosine annealing schedule. So it's like a very smooth decrease, just like the verb method. So it will smoothly decrease LR to a minimum value and it will increase it again. So so just know that these methods exist. You don't need to dive very deep into it, but just know that you can schedule your learning rates like such. And then you have some fine-tune strategies. So this process of freezing the pre-trained layers and using your model for specific use cases is known as fine-tuning. So seven fine-tuning. So our first method is actually what we just did earlier. So strategy one is train only final layer, which is exactly what we are doing. So our strategy one was actually training only the final layer, and it's actually the fastest method. It needs the least data and is good for similar tasks to ImageNet. So we use only the final layer. What we did earlier is using only the final layer, and it's good for similar tasks to ImageNet models. And then the strategy two is to unfreeze the last few layers instead of the only last layer. So strategy two. So we'll unfreeze last two layers. So let's define a function unfreeze last layers, and then we pass our model and number of layers, which you can say n or number of layers. Uh, so it will unfreeze the last number of layers in the model. So you have child counter is equals to 0. So what we did earlier, using model dot child children, you'll get the parameters from child dot parameters, and then you'll set param dot requires gradient is equals to true for those layers, and then you'll just return the model. So it's exactly what we did earlier, but in this case we are defining an if-else loop. So your child counter will increase until it crosses num layers, and for those many layers it will just put param dot requires gradient is equals to true, and for rest of the layers it will be false. So it will start from the last two n whatever number of layers you define. So it will start backwards. So this is the strategy 2, and then similar to strategy 2 is the strategy 3. So strategy 3 is unfreezing the entire model. So what it does is that it's just like uh, it will unfreeze. One second. Yeah. So it will unfreeze all the layers with different learning rates. So it's the same thing, but we define different learning rates. So it's the same thing. So you set params dot to upgrade is equals to this, and then you set different learning rates. So layer 4, layer 3, etc. So just know that this exists. You'll like pass in some different type of learning rates here, and then you can define base LR is equals to factor into factor into factor. So this is like you unfreeze all with different type of learning rates. So unfreezing all the layers with different type of learning rates, and then it's like this one has the best results. So has the best results, but it needs more data because we are using different learning rates. And use low and you should use lower LR for early layers. So in this you pass in the base LR and the factor, and when we are moving back into the layer, so if layer 4 exists, we are using base layer base learning rate, and then if we are going back in layers, we are multiplying it by a factor which will be like 0.1 or something, which will decrease the learning rate for the earlier layers. So that's what I wrote there here. So that is how you set that's how you unfreeze all the layers with different learning rates. You define different learning rates for different layers. Everything else is the same. So uh what all is left? Okay. So yeah, there's data augmentation as well. So there's data augmentation for better generalization. So if we're using an ImageNet model, like we use ResNet-18, right? So we need to make sure that we use ImageNet statistics for normalization. This we even saw in second session as to how to normalize our image according to ImageNet statistics. So let's load our ImageNet statistics. So this we saw in our second session as to how we do it. So we import a mean and standard deviation, and then let's train with augmentation to create more data. So with augmentation. So let's define our transformation pipeline. So train underscore. So train underscore transforms is equals to transforms dot compose. This is the exact thing that we saw earlier, if you remember. So transform.compose is for appending different type of transformations. So we have transform.random resize, so it will randomly resize. And then we have random horizontal flip dot to tensor, converting it to tensor. And then we have normalize, for example. So these are different type of transformation. We can even use random crop, random resize crop. So random resize crop is a combination of resizing and cropping, and then we can even use like we can even jitter colors. So there are different type of transformations that you can use. Dot color jitter or something. Yeah. So you jitter by inputting brightness, contrast, saturation, hue. So these are different type of color jitterness that can apply to a picture itself. And then you have some validation and test dataset. So you only apply augmentation to the training dataset for creating more data, but you create validation without augmentation. So you don't apply any augmentation here. So there's no random resizing or random center cropping or anything. So it's no augmentation. And then uh, yeah, so these are different type of transformations that you can apply. So when you need to apply to your training data, so you can call your data on these transformations, and in a sequence wise your data will be transformed accordingly. Now, yeah, we saw about learning rate scheduling as well. So step LR, reducing on plateau. Okay, so let me lastly tell you about some pre-trained models here. So as we saw earlier about ResNet-18, let me just show you how we call them. So ResNet-18 is equals to models are ResNet-18, P10 is equals to true. ResNet-50, for example, has the same type of calling. So ResNet-50 is equals to models or ResNet-50, and then you have mobile VNet underscore 2, mobile unders mobile net sorry mobile net v2. So you use models at mobile net v2, pretend is equals to 2, and you can even load densenet. So these are different type of models that you can load. So what we saw earlier basically, let me just kill the process. So this is how you can load different type of models. And yeah, this is pretty much it for the third session. I know it's a lot of overdose, but this is a lot of content that I needed to cover for deep learning, and it's pretty much complete. So we saw that why deep learning is better. Then we saw CNN building blocks, and then we saw the output dimension calculation, and then we saw how to build and train CNNs from scratch, and then we even trained it on CIFAR10 dataset, and then we saw how ResNet's SIFT connection works, and even saw ResNet how ResNet works in detail, and then we saw how transfer learning works, how rate scheduling works, and how to debug basically. So the key takeaways from this session is how CNN automatically learns hierarchical features, and then transfer learning is a best friend for limited data, and then you should even monitor training costs for debugging. So this is something you can look up. I think I did put it in the PDF itself. Okay. So, and the last thing is that you can start with a pre-trained model before building from scratch. So this is your third assignment. So like just like you did for second assignment, you need to build a cat versus dog classifier using ResNet-18, and you need to perform some data augmentations and use learning rate scheduling and achieve 90% accuracy. I hope it's clear. If you have any doubts, do let me know and we'll discuss it over WhatsApp. Thank you.